On the 1st of June, 1942, inside a converted automobile plant in Willow Run, Michigan, the temperature on the factory floor reached 112 degrees Fahrenheit. The men and women working the B-24 Liberator bomber line were soaked through their coveralls before the first hour of the morning shift ended. Tools slipped from sweating hands, tolerances drifted. Aluminum panels that had been measured to 1,000th of an inch in the cool hours of early morning did not fit the same way by noon. Foremen walked the line with clipboards and worried faces, counting the number of units rejected by final inspection. Henry Ford had promised the Army Air Forces one bomber an hour. What he was delivering that summer was something less than one a day. 3,000 miles to the east, in the optical workshops of Carl Zeiss in Jena and the precision instrument factories of Hugo Schneider in Leipzig, German engineers were producing some of the finest optics and fire control instruments in the world. Their craftsmen worked in cool, stable conditions. The lenses they ground and the rangefinders they assembled were finished by hand to tolerances that astonished Allied technical teams when they captured examples in North Africa and Italy. On paper, German precision manufacturing was superior. It was also irreplaceable and impossibly slow. When a German 88mm anti-aircraft battery burned out its fire control computer in the summer of 1943, the battery waited weeks for a replacement. And sometimes it waited forever. This is the story of how a technology that most Americans in 1942 had never experienced in a workplace, and that military planners had never listed among the instruments of war, turned out to be as decisive as the tank and the bomber. It is the story of how a physicist's discovery in 1902, a cigar maker's complaint in Brooklyn, and an engineer's stubborn insistence on solving a problem no one else thought was worth solving ultimately gave the United States the manufacturing capacity to bury the Axis under an avalanche of precision weapons, produced at speeds that German and Japanese engineers, locked into their old methods, could not begin to match.
The problem that Willis Carrier did not set out to solve. In the summer of 1902, a printing plant on Sackett Street in Brooklyn, New York, was losing money. The Sackett Wilhelms Lithographing and Publishing Company printed a popular magazine called Judge, and every summer the humidity that rolled in off New York Harbor caused the paper stock to absorb moisture, expand, and throw the precise color registration of its four-color printing process out of alignment. The ink dried unevenly, the colors blurred, the press runs were wasted. The plant superintendent, a man named Irving Lyle, contacted the Buffalo Forge Company, a heating and ventilation manufacturer, and asked if anyone there could solve the problem. The engineer who took the assignment was 25 years old. His name was Willis Haviland Carrier, and he had been with the company for exactly 1 year. He had grown up on a farm in Angola, New York, graduated from Cornell with a degree in electrical engineering, and had no particular expertise in thermodynamics. What he had was a habit of thinking problems through from first principles, a tolerance for months of calculation, and a willingness to be wrong in his notebooks before he was right in his designs. Carrier understood that the problem was not temperature, it was moisture. The paper was expanding because it was absorbing water vapor from the air. To solve the problem, he had to control not just the temperature of the air in the plant, but its absolute humidity, the amount of water it contained per cubic foot. He spent months working out the psychrometric equations that described the relationship between temperature, humidity, and the dew point of air. He designed a system of chilled coils through which the plant's air could be circulated, cooling it until moisture condensed out onto the coil surfaces, then reheating it to the desired delivery temperature. He called the result the dew point control method. The patent he filed in 1906 called it an apparatus for treating air. What he did not realize, and would not fully appreciate for another decade,
was that he had not invented air conditioning for printing plants. He had invented air conditioning for everything. The silk thread and the rifle barrel. Between 1902 and 1920, Carrier's invention spread slowly through a narrow range of industries where humidity and temperature caused visible, measurable production losses. Textile mills used it to keep thread from breaking. Tobacco plants used it to keep dried leaf from crumbling. A handful of pharmaceutical companies used it to stabilize chemical reactions. The technology was expensive, and its benefits, while real, were hard to quantify in the boardroom language of the era. The equipment was large, the refrigerants were toxic, early systems used ammonia, sulfur dioxide, or methyl chloride, and the engineering required to install a system correctly was not widely available. The military application that would eventually prove decisive came from a completely different direction. In 1921, the Springfield Armory in Massachusetts, the same federal arsenal where John Hall and his successors had spent a century perfecting the American system of interchangeable manufacture, began experimenting with temperature and humidity controls in its precision grinding rooms. The problem they were trying to solve was not worker comfort. It was a phenomenon that machinists called thermal growth. A piece of steel at room temperature has a specific set of dimensions. That same piece of steel, warmed by the friction of a grinding wheel or by an afternoon sun through a factory window, has slightly different dimensions. The difference might be measured in tenths of a thousandth of an inch. For a rifle barrel, that was close enough to acceptable. For a bombsight or a gun-ranging instrument, it was the difference between a weapon that worked and one that did not. Springfield's experiments showed that a room held at a constant 68 degrees Fahrenheit, with relative humidity between 45 and 55%, produced measurements that were reproducible hour after hour, day after day, regardless of what was happening outside. The gauges gave the same readings in August that they gave in February. The parts passed or failed inspection on the basis of their actual dimensions, not on the basis of what the weather was doing. It was, in the language of manufacturing engineers, a controlled environment. And in a controlled environment, tolerances that had previously been achievable only by the most skilled craftsmen could be built into the process itself. The Ordnance Department filed this finding away in its records. For the next 15 years, in the long peace of the 1920s and the deepening depression of the 1930s, almost no one acted on it. Knudsen's second condition. When William Knudsen accepted Franklin Roosevelt's offer to run American war production in the summer of 1940, he brought with him the manufacturing philosophy he had developed over 4 decades at Ford and General Motors. The philosophy had 2 pillars. The first was the one he stated publicly and often. Accuracy is the only straight line to greater production. The second was one he enforced quietly, through the contracts his office let and the specifications his engineers wrote into them. It could be stated simply. Accuracy requires a controlled environment, and a controlled environment requires air conditioning. Knudsen understood something that his critics in Congress, who were busy accusing him of favoring his former employers in the auto industry, did not. The problem with American war production in 1940 was not raw industrial capacity. The country had plenty of steel mills, machine tool plants, and workers who knew how to use them. The problem was that almost none of those facilities had been designed to produce weapons to military tolerances. An automobile engine is a marvel of industrial engineering, but its parts are manufactured to tolerances measured in thousandths of an inch. A Norden bombsight, the precision optical and mechanical computer that American B-17 crews would carry over Germany, required tolerances measured in 10,000ths. The gap between those 2 numbers was not a matter of skill. It was a matter of environment. Through 1941 and into 1942,
The contracts that Knudson's office let for precision instruments included, for the first time in American industrial history as a matter of routine procurement, specifications for factory environmental control systems. The plants that won those contracts had to build or retrofit air conditioning and humidity control systems in their precision work areas. The Carrier Corporation, now a major industrial firm, suddenly found itself with more government contracts than it could staff. It hired engineers from universities that had never before considered atmospheric control a serious field of study. It trained installation crews by the hundreds. By the end of 1942, Carrier was producing environmental control systems for military production facilities at a rate that would have seemed absurd to Willis Carrier himself 40 years earlier in the Brooklyn printing plant. The results appeared in the production numbers with a lag of 6 to 9 months, the time it took to install systems, retrain inspectors, and work through the initial batches of parts made under controlled conditions. But they appeared. The bombsight problem. Of all the precision weapons that the United States produced in the Second World War, none illustrated the relationship between environment and accuracy more starkly than the Norden bombsight. Carl Norden was a Dutch-born engineer who had worked for the U.S. Navy since 1920, developing a gyroscopically stabilized optical bombsight that could, in theory, allow a bomber flying at 20,000 feet to place a bomb within 100 feet of its target. The device he eventually produced was a masterpiece of precision mechanical engineering. It contained over 2,000 parts. Its main gyroscope ran at 7,500 revolutions per minute. Its gear trains were machined to tolerances of a 10,000th of an inch. The mirrors in its optical head were ground and coated at the Perkin-Elmer Corporation's facility in Norwalk, Connecticut. The Norden bombsight was also extraordinarily difficult to manufacture. The early production runs, made at Norden's plant on Lafayette Street in Manhattan, were plagued by rejection rates that at times exceeded 40%. Parts that measured within tolerance at the start of a shift were out of tolerance by the end of it. The precision grinding equipment was sensitive to floor vibration. The optical assembly area was sensitive to dust. And the entire facility was sensitive to the weather, specifically to the humid summers and dry winters of New York City, which caused the metal components to expand, contract, and shift in ways that made repeatable precision nearly impossible. The solution came in stages. Perkin-Elmer, which was producing the optical components, installed full environmental controls in its precision areas in 1941. The temperature in the optical grinding rooms was held to within half a degree of 68. Norden's main assembly plant in Manhattan was a harder problem. The building was old, the space was cramped, and the structure made retrofitting a full environmental control system difficult and expensive. The Navy eventually solved this by building a dedicated production facility in Indianapolis, designed from the ground up for controlled environment manufacturing. By 1943, the Indianapolis plant was producing Norden bombsights at a rate and quality that the Manhattan facility had never approached. The Germans knew the Norden existed. Their intelligence services had obtained partial technical information about it before the war through an agent named Hermann Lang, a Norden employee who passed drawings to the Abwehr in the late 1930s. What German intelligence did not fully understand, and what the stolen drawings could not convey, was that the bombsight was not primarily a design problem. It was a manufacturing problem. Germany had engineers who could have understood the design. It did not have the factory infrastructure, the environmental controls, the gauge tradition, the supplier network of precision grinding shops operating in controlled rooms that would have been required to produce it in quantity. The desert that decided everything. On the 8th of November, 1942, the same morning that the keel plate of the SS Robert E. Peary was being laid in Richmond, California, American and British forces were landing on the beaches of French North Africa.
Operation Torch had opened the Mediterranean theater, and with it came a problem that military planners had underestimated and that quartermaster and ordnance officers would spend the next 8 months trying to solve. The North African desert was destroying American equipment at a rate that alarmed everyone who saw the maintenance reports. Sand infiltrated engine air filters, ground down cylinder walls, and turned hydraulic fluid into abrasive paste. The heat, regularly exceeding 110 degrees Fahrenheit in the Tunisian summer, caused rubber seals to fail, lubricants to thin, and electronic equipment to behave erratically. Radios that had been calibrated in the comfortable shops of New Jersey drifted out of frequency alignment when their components expanded in the desert heat. The British had been fighting in the desert since 1940 and had developed workarounds: thicker air filters, specialized lubricants, modified maintenance schedules. The Americans arrived with equipment designed for temperate conditions and had to learn quickly. But the deeper problem was not in the field. It was in the factories. The electronic equipment failures in North Africa prompted a series of urgent investigations by the Army Signal Corps, which traced many of them back to a single cause: components that had been manufactured and tested at room temperature in American factories, then shipped into an environment where they were subjected to temperatures 50 to 80 degrees higher than anything their manufacturers had anticipated. Capacitors changed value, resistors drifted, solder joints that had been inspected and passed at 70 degrees developed microfractures when they cycled between the cold of a desert night and the heat of an afternoon in a vehicle that had been sitting in the sun. The Signal Corps response was methodical and, in retrospect, decisive. Beginning in late 1942 and accelerating through 1943, Signal Corps procurement specifications for electronic components began including environmental qualification requirements. Components had to be tested not just at room temperature, but across the full range of temperatures and humidities they might encounter in service, from the cold of high-altitude flight to the heat of a desert vehicle. Manufacturing facilities producing Signal Corps components were required to install the environmental controls necessary to produce consistent parts under controlled conditions, so that the parts produced in January would behave identically to the parts produced in August. The Carrier Corporation and its competitors, York, Trane, Frigidaire's commercial division, found themselves being asked to design not just comfortable factories, but factories that could function as precision instruments in their own right. The controlled environment was no longer a luxury or a concession to worker productivity. It was a manufacturing specification, written into federal contracts with the same authority as a materials standard or a dimensional tolerance. What Japan could not copy. While the American defense industry was embedding environmental control into the foundations of its production system, Japan was attempting to solve a different and, in some ways, even harder problem. Japanese precision manufacturing in 1941 was, in selected areas, genuinely excellent. The Mitsubishi Type 96 and Type 1 torpedoes were regarded by American naval engineers, when they examined captured examples, as superior in reliability and performance to anything the U.S. Navy had in service. The Zero fighter's airframe was beautifully made. Japanese optical instruments, particularly naval binoculars and rangefinders, were considered by many analysts to be among the finest in the world. But Japanese production was built on the same craftsman-centered model that had hobbled German manufacturing. A skilled worker at a Mitsubishi plant in Nagoya did not use a gauge. He used his hands, his eye, and his experience. The parts he produced were excellent. They were not interchangeable. This distinction, invisible in peacetime, became catastrophic in war. After the Battle of Midway in June 1942, Japan lost 4 fleet carriers and, more importantly, a large fraction of its trained aircrew. The pilots who had flown off Akagi and Kaga and Soru and Hiru could not be replaced in months. Neither could the aircraft maintenance personnel, the instrument calibrators, the torpedo technicians. Japan's manufacturing system was a system of people, and the people could not be mass-produced. The Americans and the Japanese were not fighting the same kind of war. Japan was fighting a war of skilled assets, carefully husbanded and irreplaceable. America was fighting a war of systems and environments, of factories held at 68 degrees, of gauges that could be read by workers who had been on the job for 6 weeks, of specifications precise enough that a replacement part shipped from Detroit could be installed by a mechanic in Guadalcanal without a file or a micrometer. The Japanese Naval Air Arm understood something of this by late 1942. Intelligence reports and captured documents gave them a picture of American production rates that, if accurate, described a situation they could not overcome. In November 1942, a Japanese industrial assessment team concluded that the Americans were producing aircraft at a ratio of approximately 5-to-1 over Japanese production. This was slightly optimistic for the Americans. The true ratio at that point was closer to 3-to-1, but the trend line was clear, and the Japanese assessment team knew it. They recommended urgently that Japan adopt mass production methods for aircraft manufacturing. The recommendation was never effectively implemented. The reasons were many: shortage of machine tools, shortage of aluminum, the disruption of the American submarine campaign against Japanese shipping. But among the reasons that technical historians have subsequently identified was one that no Japanese industrial planner in 1942 fully appreciated. Mass production to military tolerances requires environmental control, and environmental control requires refrigeration equipment, electrical capacity, and an engineering infrastructure for climate systems that Japan simply had not built. You cannot decide in 1942 to install the manufacturing environment that you failed to develop between 1920 and 1940. The lead time is years, not months. The fuse that won the war. In the autumn of 1940, a British technical mission arrived in Washington, carrying, among other things, a leather suitcase. The suitcase contained what the historian James Finney Baxter would later describe as the most valuable cargo ever brought to American shores. Among the items in the suitcase was a prototype of the cavity magnetron, the device that made centimetric radar possible, and the technical details of several other advanced weapons developments. It also contained the specifications for a device that the British had been working on since 1939 and had largely failed to produce in quantity: the variable time fuse, also known as the proximity fuse. The proximity fuse was a small radio transmitter and receiver built into an artillery shell. It emitted a continuous radio signal, and when the reflected signal from a nearby object, an aircraft, the surface of the water, the ground, shifted in a way that indicated the target was within lethal range, a tiny electronic circuit triggered the shell's explosive charge. For anti-aircraft fire, it was transformative. Instead of requiring a shell to physically strike an aircraft or detonate within a precisely calculated distance, the proximity fuse turned every near miss into a kill. The British had the concept. What they could not do was manufacture the proximity fuse at scale. The device contained a miniaturized vacuum tube that had to survive being fired from an artillery gun, an acceleration of approximately 20,000 Gs, and then function as a precision electronic instrument. The tubes were small enough to fit inside a shell casing. They had to be manufactured by the millions. Each one had to work. The National Defense Research Committee assigned the proximity fuse project to a team that included engineers from Johns Hopkins, Sylvania, Western Electric, and RCA. The manufacturing problem was handed to Sylvania's Emporium, Pennsylvania plant and to a new facility at the Naval Ordnance Laboratory in Silver Spring, Maryland. What those engineers discovered over 2 years of production development was that the miniature tubes could only be manufactured reliably in a controlled environment. The glass-to-metal seals that held the tube's electrodes in alignment were sensitive to temperature changes during the sealing process. The electron-emitting cathode material was sensitive to atmospheric moisture during assembly. The completed tube's calibration drifted if it was tested in a humid room and then stored in a dry one. Every step of the manufacturing process, from the initial glasswork to the final electrical test, required temperature and humidity control. Sylvania retrofitted the Emporium plant at a cost that the company's post-war financial reports described as substantial. Carrier engineers spent months designing the specific environmental zones required for each stage of production. The result was a factory that was, in effect, a precision instrument, a building whose internal atmosphere was as carefully controlled as the products it made. By late 1942, Sylvania and its production partners were producing proximity fuses at rates measured in the tens of thousands per month. By 1944, monthly production exceeded 1 million units. The fuse was used first in naval anti-aircraft guns in the Pacific, where it dramatically increased the kill rate against Japanese air attacks. It was used in the Battle of the Bulge, where American artillery fired proximity-fused shells that exploded above German infantry formations in the Ardennes, producing casualties that a ground-burst shell could not have achieved in the same wooded terrain. German engineers who examined recovered American shells understood the technology. They could not reproduce it. Their precision tube manufacturing, even in the best workshops in the Reich, could not hold the tolerances required. The environment in which those tolerances had to be held did not exist in German industrial facilities at the scale required. The men in the white coats. In the spring of 1944, an Army Air Forces inspection team visiting a B-29 production facility in Wichita, Kansas, noted something in their report that would have seemed unremarkable by then, but would have been incomprehensible to a manufacturing engineer of 1920. The team observed that the plant's precision assembly areas were staffed in significant part by women who had been recruited from local schools and given 6 weeks of factory training. These workers were assembling fuel system components and electrical harnesses to tolerances that, before the war, would have been achieved only by journeyman machinists with years of experience. They were achieving those tolerances reliably, shift after shift, because the environment in which they worked, the temperature, the humidity, the cleanliness of the air, was held constant by systems that removed the variables from the manufacturing process. This was Knudsen's deepest insight, expressed not in words, but in contracts and specifications. Precision was not a gift of the craftsman's hands. It was a product of the system in which the craftsman worked. Control the environment, and you could train anyone to produce precision parts. The precision lived in the gauges and the controlled atmosphere, not in the worker's accumulated skill. You could replace the worker, you could not replace the system. Germany could not replace the Facharbeiter, the skilled craftsman, quickly enough to meet wartime production demands. It tried. Albert Speer's armaments ministry, after 1942, pushed hard for production rationalization, for standardized parts, for reduced model variants. It achieved real gains. German production of tanks, aircraft, and artillery all increased substantially through 1943 and into 1944, even as Allied bombing grew more intense. But the gains were achieved by working the craftsmen harder and longer, not by substituting a system for their skills. And a craftsman can work only so many hours before his hands tire and his eye loses its precision. A controlled environment does not tire. The avalanche. When the war in Europe ended on the 8th of May 1945, the United States had produced, since Pearl Harbor, approximately 300,000 military aircraft, 86,000 tanks and self-propelled guns, 71,000 naval vessels, 2,710 Liberty ships, and more than 40 billion rounds of small arms ammunition. The numbers are so large that they lose meaning quickly. What they represent, stripped of the zeros, is a manufacturing system that had learned, through 40 years of accumulated practice, through the gauge tradition that John Hall had begun at Harper's Ferry and that Knutson had enforced across an entire wartime economy, to produce precision at the speed of a moving assembly line. The air conditioning that was part of that system is the invisible infrastructure of the American victory. It does not appear in the official histories. It does not appear in the production statistics. You cannot photograph a controlled atmosphere or film a humidity specification being enforced. But it was there, in the optical rooms of Perkin-Elmer and the fuse assembly areas of Sylvania and the instrument shops of the Springfield Armory and the tank engine plants of Detroit. It was the reason a replacement part dropped into an engine bay without filing. It was the reason a proximity fuse survived 20,000 Gs and still functioned. It was the reason the bombsight in the nose of a B-17 over Schweinfurt could hold a calibration that had been set in a factory in Indianapolis 6 months and 10,000 miles earlier. Willis Carrier, in 1902, was trying to keep paper from wrinkling in a Brooklyn printing plant. He could not have known that what he was actually doing was giving the American defense industry the ability to manufacture precision where previously only skill could produce it, to move that precision from the hands of craftsmen into the walls of buildings, and to hold it there, steady and reliable and scalable, across the most intense industrial effort in human history. The war, in the end, was not won by the better tank or the better submarine. It was won by the better factory. And the better factory, above all else, was a place where the temperature was controlled, the humidity was specified, and the gauges read the same number in January as they did in August. Germany had Daimler and Krupp and Zeiss. It had engineers who had given the world some of its finest technical achievements. What it did not have, what it had never built, because no one had understood in the 1920s and 30s that it would matter, was the institutional infrastructure of controlled manufacturing environments, embedded in 10,000 factories, enforced in 1 million procurement contracts, and built into the habits of a production system that had been learning since Springfield and Harper's Ferry and the Crystal Palace exhibition of 1851 that accuracy is the only straight line to greater production. America had been building that environment for 40 years before the war began. When the war came, it was ready.